the last chapter, we touched on cross-price effects, and so this time, we'll look more closely at demand relationships between goods. Starting with a simple two-good case, we want to think about the impact of a decrease in the price of Y on the quantity demanded of X. As always, we're going to have both an income effect and a substitution effect. If we think about the income effect, a decrease in the price of Y increases the consumer's purchasing power, and so that should mean that their consumption of both X and Y should go up. But on the other hand, a decrease in the price of Y means that Y is now cheaper relative to X. That means that the consumer is going to substitute away from X and towards Y. Depending on which of these two effects is stronger, the overall effect on X could be either positive or negative. We can summarize this by looking at the Slutsky equation for cross-price effect. So here we have del X, del Py, and we can decompose that into del X, del Py, fixing our utility level, so that's a substitution effect, minus Y times del X, del I, which gives the income effect. The substitution effect is going to be positive, while the income effect is going to be negative. So the overall effect depends on the balance of these two. As with the usual Slutsky equation, we can also write it in elasticity terms. So we can write the cross-price elasticity of X with respect to Py is equal to the compensated cross-price elasticity minus the share of income spent on Y times the income elasticity of X. In this diagram, the graph on the left is going to show two goods that are gross complements. If I decrease the price of Y, that's going to shift the budget line from I0 to I1. That's going to cause the demand for both X and Y to increase so that del X, del Py is less than 0. On the other hand, the graph on the right shows two goods that are gross substitutes. As the same price drop caused the demand for Y to increase, but the demand for X to decrease, so del X, del Py is greater than 0. If I have a Cobb-Douglas utility with equal coefficients like this, then from what we found in the last couple of chapters, the uncompensated demand for X is I over 2px, while the compensated demand is given by the square root of py over px times u bar. We can see that py doesn't appear in the compensated demand equation. So the overall effect of a change in the price of Y on the demand for X must be 0. But if we use the Slutsky decomposition that we found earlier, we can show that this is because there are income and substitution effects of equal size that exactly cancel each other out. If we look at the substitution effect, we have that del xc del py is equal to 1/2 over the square root of px py times u bar. And then, by duality, we have that u bar is equal to the indirect utility, v, which for Cobb-Douglas is I over 2 times the square root of px py. So we plug this expression in for here, we get I over 4 px py. If we look at the income effect, that's going to be minus y times dx di. Well, analogous to the demand for x, the demand for y is going to be I over 2py. And the demand for x If I take the partial derivative with respect to I, that's just going to be 1 over 2px. So here I have minus I over 4px py. So here we can see that the income and substitution effects are exactly the same size, and if I add them, I get an overall effect of 0. So if I change the price of y, there's going to be no overall effect on the demand for x. In the case where I have n goods, I can write the Slutsky equation for any pair of goods. So I can find the change in the demand of xi in response to a change in the price of good j. That's going to be equal to the effect holding the utility constant, so that's a substitution effect, minus xj times del xi del I. That's going to be the income effect. And once again, I can write this as an elasticity. So epsilon xi pj is equal to the compensated elasticity minus the share of income I spend on j times the income elasticity. Intuitively, we can think about substitutes as being goods that can replace each other. So think about Coke and Pepsi or butter and margarine. If you increase the price of one of these, that means you're going to buy more of the other one instead. On the other hand, complements are goods like peanut butter and jelly or baseballs and baseball bats. An increase in the price of one of these means that you're going to be buying less of both. These are goods that go together. If we're using the uncompensated demand function, we can define two goods to be gross substitutes if del xi del pj is greater than 0, and gross complements if del xi del pj is less than 0. When we're talking about gross substitutes and gross complements, these definitions are not symmetric. So just because this is positive doesn't mean that del xj del pi has to be positive. These are not equivalent conditions. So it's possible that x1 is a substitute for x2, but x2 is a complement to x1. For example, let's suppose we had a consumer with utility log x plus y. So we can set up Lagrangian log x plus y plus lambda times I minus pxx minus pyy. That's our usual utility maximization Lagrangian. So we have the first order conditions. 1 over x minus lambda px is equal to 0. 1 minus lambda py is equal to 0. And taking the derivative with respect to lambda, just like it always does, just gives us back the budget constraint. So to solve this, we have that py is equal to px times x equals 1 over lambda. If we plug this into the budget constraint, we get that pxx plus pyy is equal to py times 1 plus y is equal to income. And so if we solve that, we get that y is equal to I minus py over py. And then from this equation, we get that x is just equal to py over px. What these demand functions mean is that this consumer is going to look at the relative prices of x and y and use that to determine how much x to buy regardless of how much income they have. So they're going to buy a fixed amount of x depending on the relative prices, and then they're going to spend the remainder of their income on y. So whatever money they're not spending on x, is being spent on y. If I look at the cross price effects, del x del py is 1 over px, which is positive. That means that x is a substitute for y. But if I look at del y del px, well, px doesn't show up in this equation, so that's equal to 0. So that demonstrates that these definitions are not symmetric. Right? X is a substitute for y, but y is not a substitute for x. Alternatively, we can define complements and substitutes using the compensated demand functions, which means we only look at the substitution effects. So from Shepard's lemma, we have that del xi del pj is equal to the second derivative of the expenditure function with respect to pi and pj. But because the order of differentiation doesn't matter, this is also going to be equal to del xj del pi. What that means that if one of these is positive, the other one must be positive. If one of them is negative, the other one must be negative. So, unlike with gross substitutes and gross complements, if xi is a net substitute for xj, then xj is a net substitute for xi, and likewise if they're complements. However, if we're using net substitutes and complements, this definition is actually not as useful because by Hicks's second law of demand, most goods are substitutes. The compensated demand function is going to be homogeneous of degree 0 because if I multiply all of the prices by the same factor, the demands won't change. So by Euler's theorem, what I have is if I take the product of each argument with the corresponding partial derivative, and I sum all of those up, because x is homogeneous of degree 0, that's going to equal 0. And then if I just divide both sides by x, what I have is that I have the sum of all of the price elasticities from P1 up to Pn is equal to 0. So what does this mean? Well, if I take a look at the own price elasticity, the own price elasticity is typically negative because I should have a downward sloping demand curve. That means if I sum up all of the cross price elasticities, these are all going to sum up to something positive. Now, it doesn't mean that individual terms can't be negative. So there may be some goods that are in fact complements to xi. But overall, because the sum of the cross price elasticities must be positive, most goods are going to be substitutes for xi and not complements. So far, we've taken for granted that there was a clear definition of what constituted a separate good. But depending on what exactly we're looking at, how to classify goods can be rather difficult, since different brands of snacks, or movie tickets at different showtimes, or any other seemingly minor distinctions might justifiably be treated as distinct. However, dealing with a large number of goods gets increasingly more complex as we need to consider substitution effects for every pair of goods. So we're often going to aggregate goods into general categories like food or clothing. So if we have n goods, we might want to simplify our analysis by just considering the trade-offs between x1 and everything else. So we can think about all of the goods x2 through xn as just some composite commodity y. And so we can define a price for each x good. So we know the price of x1, And then to figure out the price of the composite commodity Y, we need to assume that the relative prices of all of the goods x2 through xn stays fixed. If we hold the prices of all these goods fixed at their initial values of P2 naught up to Pn naught, we can just define the composite commodity Y as the total spending on everything except for x1. So that my budget constraint becomes P1 x1 plus y. In order to use this composite commodity, we need to assume that all of these prices, P2 through Pn, move together. So let's say that they were all to increase by a factor of t. That would just change my budget constraint to P1 x1 plus t times y. So the prices of all of these components has increased by the same factor. And then I can look at the substitution effects that are induced when I either change the price of good 1 or I change this factor t, which is going to affect the price of everything else. So let's suppose we have an individual and we can divide their consumption into 3 broad categories. X is food, Y is housing, and Z is household operations like electricity. And let's say that they have a CES utility. So the utility is minus 1 over X, minus 1 over Y, minus 1 over Z. So if we set up the Lagrangian, we have the utility function plus lambda times I minus pxx minus pyy minus pzz. If we take the first order conditions, we have del L del x is equal to 1 over x squared minus lambda px is equal to 0, or we can write this as 1 over lambda is equal to px times x squared. And because the first order conditions will be the same for y and z, I can also write that this equals py y squared, which also equals pz z squared. From these, we can get that y is going to be equal to the square root of px over py times x, and that z is going to be equal to the square root of px over pz times x. So if I substitute these two back into the budget constraint, I get px x plus the square root of px py x plus the square root of px pz x is equal to I, or x is equal to I over px plus the square root of px times py plus the square root of px times pz. And by symmetry, we have that y is given by this, and z is given by this. If we start with an income of 100, where px is equal to 1, py is 4, and pz is equal to 1, then x star is going to be 100 over 1 plus 2 plus 1, or 25. And likewise, y star is going to be 12 and a half, and z star is going to be 25. We can continue to consolidate this by combining y and z. So y was your housing spending, and z was your spending on household operations. We could just combine this into a composite housing commodity, where H is just your total spending on y and z, or 4y plus z. So if we're combining y and z like this, we have to assume that py and pz are always going to move together. And we can define ph as equal to pz or py over 4. If we plug this back into the demand function, we're going to get that x is equal to I over px plus 3 times the square root of px times ph. So, given these three initial prices, by our definition, ph is going to be pz, which is 1. And then if I plug that into here, I get once again that x is going to be 25 and h is going to be 75. So far, we've assumed that once a good is bought by a consumer, it's consumed and directly gives you some utility. But often this isn't the case. Often what we're buying are instead ingredients that we then have to use to produce something ourselves, so some type of household production. And then the products of this household production are going to be what's going to give us utility, not what we bought. So let's, for example, think of x, y, and z as flour, butter, and sugar. And so while we could just eat these directly, that's probably not a good idea. Instead, we want to think about all of the different things that we can bake using different combinations of these ingredients, like cake and cookies or whatever else. And those are what are going to give us utility, not the ingredients. So we're going to have household production functions. A1 and A2 are going to be the things that we can produce using these ingredients, and then our utility is going to be a function of our consumption of A1 and A2, not of the ingredients. The household production functions here are going to define a trade-off between the consumption goods, because devoting more ingredients to making A1 means that we have less ingredients to devote to A2, and therefore we'll produce less of it. One simple form of the household production model is to assume that instead of consuming goods, we're consuming attributes, and these attributes are present in everything we consume in some measure. So, for example, we're not so much consuming food as we are consuming protein and carbohydrates. Everything we eat is going to have some amount of either one. So we can model this using linear production functions. So A1 is equal to AX1 X plus AY1 Y plus AC1 Z, and B2 is going to be defined similarly. And these are going to be the amount of that nutrient that's present in each of these goods, X, Y, and Z. In this diagram, the lines labeled X, Y, and Z represent the amount of each attribute received by consuming a single good exclusively, with X star, Y star, and Z star representing the quantity that can be afforded if the consumer were to spend all of their income only on that good. Then, the budget set is given by the shaded triangle, and we can see here that the consumer will be best off either buying a combination of X and Y or a combination of Y and Z, as any bundle that mixes X and Z or all three goods together is going to be strictly worse than that. So the optimal bundle will either look like E or E prime. Similar to what we see with linear utility functions, corner solutions will be relatively common since the consumer will want a balance of attributes. But when choosing among goods, they will just try and find the most cost-effective means of getting there. The solutions can also change quite suddenly. In the previous example, if the price of Y were to increase, moving Y star down the line, then at some point the triangle would flip, meaning that the consumer could suddenly go from consuming exclusively Y to consuming no Y. This is the end of our treatment of consumer theory. So now we need to look to the other side and start considering the producer's optimization problem.